Did you know that a tiny uranium pellet, about the size of a coin, can generate enough energy to power an entire neighborhood for a whole year? It sounds like science fiction, but it's completely real. Nuclear power plants harness the power hidden at the heart of the atom to produce colossal amounts of electricity without emitting smoke or polluting gases. In this video, you will discover how a nuclear power plant really works, what happens inside a reactor, and why this technology, although powerful, requires absolute control to keep the world powered safely. Although nuclear energy is a fundamental part of the energy mix in many countries today, the discovery of its key principle, nuclear fission, occurred less than a century ago. In 1938, scientists Lisa Meitner and Otto Hahn succeeded in unraveling one of the deepest mysteries of the universe. The nucleus of the atom could be split into two smaller parts, releasing a gigantic amount of energy. This discovery forever changed the history of science. For the first time, humanity understood that the heart of matter held a power capable of transforming entire civilizations. The most commonly used element for harnessing this energy is uranium-235, an extraordinarily powerful substance. A single pellet of this material is equivalent in energy terms to more than 80 tons of coal. This ratio makes it clear why nuclear energy is so attractive. With very little fuel, an immense amount of electricity is produced. The challenge, of course, lies in doing so safely, in a controlled manner, and in a stable way. Uranium is not used in its raw form. First, it is prepared in the form of small pellets that are inserted into long metal tubes about 50 centimeters long. These tubes are made of a special zirconium alloy, a material designed to withstand extreme temperatures and maintain its structure even under very high pressures. It does not oxidize easily, does not react with water, and acts as a perfect barrier between the fuel and the outside environment. Once sealed, these tubes are bundled together to form what are known as fuel rods. Several of these are carefully arranged inside the nuclear reactor, making up what is called the core. This core is, quite literally, the heart of the power plant. It is there that the process takes place that converts the energy of the atom into heat and ultimately into electricity. Each fuel rod has immense energy potential, capable of generating millions of kilowatt-hours throughout its lifespan. An impressive example of this type of facility is the Bruce Power nuclear power plant in Canada. Located on the shores of Lake Huron, it occupies an area of more than 9 square kilometers, equivalent to over 1,000 football fields. Within its gigantic complex operate 8 CANDU reactors, a technology developed in Canada that stands out for its safety, efficiency, and reliability. Each of these reactors can produce more than 750 megawatts of electricity, and together they supply nearly 30% of all the energy consumed by the province of Ontario. The fuel that powers these reactors is protected by multiple layers of security. Behind reinforced concrete walls 2 meters thick lies the power of the atom, completely isolated from the outside world. These barriers are designed to withstand any accident or impact and are also equipped with constant monitoring systems. Even access to the reactor area is restricted with warning signs, protective equipment, and rigorous protocols. At this stage, the uranium still emits very low levels of radiation, so it can be handled safely under specialized supervision. When it's time to start up the reactor, the fuel rods are placed inside the core with absolute precision. The reactor's internal structure is riddled with perfectly aligned holes and compartments, where each rod fits like a piece of a metal jigsaw puzzle. Technicians working in this area must wear protective suits designed to block radiation, even though the reactor can only be handled when it is completely shut down. Minimal exposure to the active core would be fatal, as the radiation released there exceeds tolerable levels for humans by millions of times. Once the core is ready and the fuel is properly installed, the chain reaction begins. Inside the uranium fuel rods, the most unstable atoms are split by being struck by particles called neutrons. At that moment, each atom breaks into 2 smaller fragments and releases a large amount of energy in the form of heat, along with several additional neutrons. These new neutrons, in turn, collide with other uranium atoms, causing further splits. This creates a continuous cycle, a self-sustaining chain reaction that releases enormous amounts of thermal energy. This process, known as nuclear fission, is the basis for the operation of all reactors. However, the real challenge is not initiating it, but controlling it. If nuclear fission were to occur without limit, the heat generated could exceed the capacity of the cooling systems, causing the dreaded core overheating or meltdown. In extreme cases, this could cause radioactive leaks and irreversible damage to the environment. To prevent this, nuclear power plants are equipped with an essential system, control rods. These control rods, made of materials like boron or cadmium, act as brakes on the nuclear process. They have the ability to absorb neutrons, reducing the reaction rate. When operators insert them into the core, fission slows down or even stops completely. In this way, a constant balance is maintained between energy production and system safety. Without control rods, the reactor would be like a runaway train with no way to stop. The reactor structure is designed like a fortress. It is not only protected by thick reinforced concrete walls, but also features automatic systems that shut down the process if they detect sudden changes in pressure or temperature. Everything is designed to prevent any accident and maintain complete control of the system. Although the energy released within the core is colossal, the reactor's aim is not to destroy, but to transform, to convert that heat into usable electricity. The heat generated during nuclear fission is transferred to a closed water circuit. This water, which never comes into direct contact with the uranium, has a single function: to transport the heat to the steam generators. It is kept under such high pressure that it prevents it from boiling even at temperatures close to 300 degrees Celsius. From a control room filled with monitors, sensors and panels, a team of engineers monitors every parameter: temperature, pressure, flow rate and reactor stability. Nothing is left to chance. Any deviation, however small, triggers alarms and safety protocols. The heat from the first circuit is transferred to a second water circuit, where the liquid is transformed into extremely high-pressure steam. This steam powers the next step in the process, driving the turbines. Meanwhile, inside the reactor, a unique visual phenomenon occurs. When charged particles travel faster than the speed of light within the water, they emit a brilliant blue glow known as the Cherenkov effect. This ghostly light, so characteristic of spent fuel pools, is the visible proof of the invisible power of the atom. The steam from the second circuit is channeled to a huge hall where the main turbines are located. These colossal structures, installed in spaces that can exceed 400 meters in length and 20 stories in height, rotate at impressive speeds, reaching 1800 revolutions per minute. The steam strikes the metal blades with force, converting thermal energy into mechanical motion. This motion turns the electric generators, which finally transform all that energy into electricity. Each generator can produce more than 750 megawatts, enough to supply 500,000 people. Once the steam has done its job driving the turbines, it isn't wasted. It's redirected to a condenser, where it's cooled by water from rivers, lakes, or the iconic cooling towers typically associated with nuclear power plants. There, the steam condenses, transforming back into liquid water and returning to the system to restart the cycle. This process repeats itself endlessly with astonishing efficiency and without releasing carbon dioxide into the atmosphere, making nuclear energy one of the cleanest sources in terms of emissions. However, one point always sparks debate: radioactive waste. After approximately 1 year of continuous operation, fuel rods lose much of their ability to generate energy. Even so, they remain extremely hot and emit dangerous levels of radiation. They cannot be handled directly or stored immediately, so they undergo a cooling and containment process. The spent fuel rods are transferred to specially designed pools filled with crystal clear water. This liquid not only dissipates residual heat, but also acts as a shield against radiation. The rods must remain completely submerged for at least a decade until their temperature and radioactivity decrease to safe levels. At the bottom of these pools, which can be more than 8 meters deep, lie thousands of spent fuel rods. Each one is a reminder of the immense power we have learned to control. Managing this waste is one of the major challenges facing the modern nuclear industry. Some countries choose to recycle part of the fuel to reuse the uranium and plutonium that can still be recovered. Others prefer to store it in highly secure underground facilities. In any case, the process requires advanced technology, constant monitoring, and an absolute commitment to environmental safety. The most fascinating aspect of nuclear energy is its ability to unite two opposing extremes: the infinitely small and the immensely large. Hidden within a single atom is a colossal force that, when released and precisely controlled, can power an entire city for years. This union of the microscopic and the monumental makes nuclear energy one of the most extraordinary achievements of modern science. On a planet desperately seeking clean, stable, and sustainable energy sources, nuclear energy plays a vital role. Unlike other alternatives, it doesn't depend on wind or sun, can operate continuously, and generates enormous amounts of electricity without releasing greenhouse gases. Its efficiency is so high that a single nuclear power plant can produce the energy equivalent of dozens of traditional thermal power plants, with a much smaller environmental impact. But this technology is not without its challenges. Harnessing the power of the atom requires absolute precision and an unwavering commitment to safety. Every part of a nuclear power plant, from the control rods to the containment structures, must operate with pinpoint accuracy, because even the smallest error could have serious consequences. That's why nuclear power plants are designed as veritable technological fortresses, where science and engineering work together to keep one of the most powerful forces in the universe under control. A nuclear power plant is not simply an energy factory, it is the symbol of an alliance between nature and technology. It demonstrates that humanity can understand, master, and harness the fundamental forces of the universe responsibly. Although its power demands respect and control, nuclear energy remains one of the clearest proofs of how far human intelligence can reach when it chooses to transform the heart of the atom into the source that drives the future.